Okay, in this video, we'll talk a little bit about potential energy and how you can use it to solve finite element equations, right? So everything we've been doing here, we've been deriving the stiffness matrices and then obviously the solutions using this direct stiffness approach where we actually get the finite element stiffness matrix from doing like sum of forces at the nodes, right? But really, sum of forces also implies an energy minimization, and it's a very powerful method, and we'll be using it for distributed loads as well. So I'm going to talk a little bit about it, and it's pretty simple with regard to springs. Okay, so let's just do it with a simple problem, okay, without getting too much into the theory, but we'll discuss the implications of the theory as we go through. Let's see if I can get this stupid thing. And there you go. All right, so let's just think of a simple two-element problem. This is, in some manner we've seen this a bunch of times already in this class. So let's put a force on here. I'll just call it F for now. We'll have two, obviously this is node 1, node 2, and node 3. Let's focus. It's a little better. And then we'll give some spring stiffnesses here. Let's call this spring stiffness K, and we can call this one 2K, so it's twice the stiffness, all right? Okay, so the idea here is we're going to write the total energy which is going to turn out to be the energy from two parts. One, it's going to be the part that's stored in the springs. We call this the strain energy. So it's the internal strain energy. And then we're going to take off of that the work done by the external forces. So this is the work now in your textbook it uses omega, and actually the way they've defined it, it's minus the external work. All right, and we'll explain why that is in a second, okay? But the basic idea is once we have the energy, the solution, and again, what we're looking for is the displacements D1, D2, D3, right? So it's the one that minimizes the total energy. And yes, this is an important distinction. Not only is it just that it minimizes the total energy, but it also has to obey or satisfy the boundary conditions, the displacement boundary conditions. Okay, sometimes we call this being kinematically admissible. Okay, so that we've got a solution that minimizes the total energy but also satisfies the displacement boundary conditions. In this particular case, it's that the displacement at node 1 is 0, or otherwise for this case, that D1 is going to go to 0, right? Hope you can't see what I'm writing. Probably need to zoom out here. All right. All right, so sometimes people are confused why the minus sign here. Well, it kind of makes sense. I mean, this energy thing, we all have a reasonable intuition with. I mean, this is sort of like the ball in the valley, right? So we all realize that where the ball will sit is the one that minimizes the potential energy, or in fact, in this gully, so to speak, right? Now, that's fine, but if we have an external force on here, right, what's going to happen? Actually, the solution won't be here, but it'll be the one where it's, in this case, I think you all physically know what's going to happen. The ball will displace up the incline until basically the y component, the contact force balances out with the gravity force, right? But here you can see obviously that it's the effect of the external force is to increase the gravitational potential energy, right? So it basically subtracts off of the minimization, okay? So it has the opposite effect of when you actually drop the position, right, which minimizes the MGH, okay? So the correct sign here would be to actually remove the energy of the external work. Or another way you can think of it is you have this energy that's applied by the external forces, right? And that one, doesn't count against the total minimization to move it up the hill, so to speak, okay? So that's what we have. Or again, like in the book, I use it this way, but the book writes it in this form where omega is defined in the negative sense. It's going to be the same exact thing. It's just the minus sign, but I don't know. I'm used to thinking of it in terms of this, all right? So you can use either or. You will get the same result. It doesn't matter, okay? And this, of course, we'll show it later on, gives you the same result as the finite elements, okay? All right. So let's go back to this particular problem, all right? And let's write the strain energy, U. This is going to be the one due to the spring forces, right? So we have two of them. So the internal energy, we know strain energy is 1/2 kx squared, right, for a linear spring, right? So for the first spring, it's 1/2. The spring stiffness is K, and its stretch is going to be D2 minus D1 quantity squared, right? I should probably put as a reminder here, right? This is the strain energy for the first element, which is going to be 1/2 the stiffness of the first element times the stretch of the first element squared, right? So you can see this is the stretch of the first element, and we've just squared it. Now we do the same for the second element. Now we've got a 1/2, but the second element has a stiffness of 2K, and its stretch is going to be D3 minus D2 quantity squared, okay? So again, this is for the second element, all right? And obviously the 2's cancel out and all that stuff. Okay, so there we go. Now what's the work of the external forces, right? So the work done by the external force in this particular case, we have one external force, that's F, and its work is the force times the displacement that force sees, so that's the displacement at node 3. So it is just going to be the force times D3, all right? Or if you want to do it like in the book, they will say omega equals minus F D3, all right? Okay, so now we have the total energy. Which is going to be the internal, the spring strain energy, right? K on 2 D2 minus D1 squared plus K d3 minus d2 squared minus f times d3. All right, so we want to find the solution that minimizes this with respect to d1, d2, and d3. Now, we have to be careful about this because we have to go back and read the statement, right? Not only does it have to minimize the total energy, but it needs to satisfy the displacement boundary conditions, all right? So that's really important. So in this particular case, it's very easy to see that. In this case, that means is that D1 is going to go to 0, right? So if the displacement of the first node is 0, then you satisfy that boundary condition, that displacement boundary condition. All right. Now we have two unknowns, D2 and D3, all right? And the cool thing about doing these energy methods, they're easy to write out here because you have one scalar energy equation. They're usually easy to write out. You don't have to worry too much about directions of forces and force vectors, so that's a nice thing. But we need to have two equations to solve, but this is a system of two variables, so that means we can consider the partial derivative with respect to D2 equal to 0, and the partial derivative of the total energy with respect to D3 equal to 0. So these are going to be our two equations, and we'll do that in a second, but I think you can all remember that from like physics 1, that, you know, or I guess actually calculus 1 as well, right? Or maybe calculus 3, I forget, where you do multivariate calculus, right? So to find the local minimum, right, we take the first derivative with respect to all the dimensions of the problem. In this case is D2 and D3. So you'll always get this. If you have n unknowns in your potential energy, your one single scalar potential energy, you want to minimize that, so you'll be able to take the derivatives with respect to every unknown. And set it equal to 0. And so if you have n degrees of freedom, that's going to give you n equations. They're going to be the same as the finite element equations that we got using the direct stiffness approach, okay? All right. All right, let's do that. Okay, and then maybe I'll stop the video there before I get too much further, because I do want to make some comparisons. All right, so here we are. All right, so there's our total energy. So if we take the partial derivative with respect to D2, what do we get? Well, I get the 2 comes down here, and I get the 1 here, so I get K times D2, right? And then doing chain rule, the derivative of the inside there is just going to be 1, so that's what you have, right? Now, take the derivative of this term with respect to D2, so I'm going to get a 2K times D3 minus D2, and then the derivative inside gives me a minus 1, right? And then the last term does not involve D2, so that's nothing, and we're going to set that equal to 0, okay? So in other words, I've got, let's combine these terms here. So I got a 2K, and then I got a minus and a minus, so this is going to give me 3K times D2 plus 2K times D3 equals 0, okay? That's going to be my first equation, all right? Now let's do the same thing with respect to the displacement at the third node, all right? And so the first term gives me nothing. The second term will give me 2K D3 minus D2 multiplied by a positive 1, all right? So that doesn't do anything. And now the last term, right, this term here, okay, it's going to give me a minus f, right? Minus f, and that all equals 0. And so we can rearrange this again. Minus 2k plus, I'm sorry, d2 plus 2k d3 equals f. And this is my second equation, all right? This is my second equation. And so again, we have two equations for two unknowns, so you can solve for this. But let's write it in matrix form, and then you'll see what's going on here, right? So if we write this in matrix form, the first equation we put in the first row, Okay, second equation we'll put in the second row. The coefficients we're solving for are D2 and D3, and that'll be equal to some right-hand side. For the first equation, the right-hand side is 0. For the second equation, the right-hand side is f, right? And so here you go. What's the coefficient of D2 in the first equation? It's going to be 3k, and the coefficient, oh, I made a mistake up here. I'm sorry. So when I did this one, sorry about that. The D3 term, I got 2k, but I got the -1 here. So actually this really should be a negative. Sorry about that. The other one looks correct, right? So then I get a minus 2k. Now for the last equation, second equation, right? We get a 2k is the coefficient times the D2 term with a minus sign, and then a 2k as the coefficient for the D3 term, right? So this becomes my system of finite element equations, okay? So you can solve for that for D2 and D3, okay? Now what you'll see is that, in fact, right, if you go back and do direct assembly, something like that, I won't be able to show, well, maybe I can. Right, if we were to look at this problem and use direct assembly, right, what would we have? Okay, well, first I'm going to have a 3 by 3, right, because I got D1, D2, and D3, and that equals the unknown reaction force at F1, 0 at the second node, and then F at the third node, right? Okay, so the first, we got 3 equations. All right. So they're going to sit like there. The first stiffness matrix is going to sit right here because it relates the sum of forces at node 1 and 2 with the displacements at node 1 and 2. So we just put the stiffness matrix here, which is a K, minus K, minus K, and then K. And then we add in the second element, right, which is going to relate the force balance at node 2 and node 3 with the displacements at node 2 and node 3. So it has a spring stiffness of 2K, so I get a plus 2K here, a minus 2K here, minus 2K here, and then a 2K here, and then obviously 0 and 0, right? This is really weird. I don't know why. The paper is bumping up, so it makes it difficult to show. But that's 2K, right? Minus 2K, all right? And now what do we normally do? Normally we say, well, the first displacement has a value of 0, so that cancels out the effect of that column. And we really don't need the first equation because we know D1 is 0. And so we're left with just this reduced system, right? There's that reduced system, which you can see is exactly the same, right? That's exactly what we got up here. All right, all right. So it's obviously it's equivalent, and so it's kind of a useful way to do it. Like I said, we'll use this trick also when we talk about doing distributed loads, and also when you do more complicated elements. It's difficult to do the force balance. You know, we're talking about hexahedral and tetrahedral elements, so the energy is a much more convenient type of approach. Okay?